This is section 10.7, part 3. We're doing complex numbers still, and we're going to be working on dividing complex numbers today, objective 4 and objective 5, simplifying powers of I. So we're going to start off with dividing them. And the rules apply to complex numbers similar to that of square roots. You cannot have a square root in the denominator. Similar to that is you cannot have a I in the denominator. And so we're going to use a very similar concept to what we did with square roots. And that is we're going to use conjugates to get rid of the I in the denominator, just like we used conjugates to get rid of the square root in the denominator. So if it is, well, let's look at what this says. It says, it is possible to multiply imaginary numbers and obtain a real number. It says, here is an example. And we're going to go through this example. If we use the conjugate of 4 plus 7i, which is 4 minus 7i, if we multiply those two conjugates, and we actually FOILed them out, you would have 4 times 4, that is 16, and 4 times negative 7i, that is negative 28i, and then 7i times 4, that would be plus 28i, and 7i times a negative 7i would be minus 49i squared. And you can see the minus 28i and the plus 28i, these two are going to cancel out, and we will have 16 minus 49, and we got an I squared, which we know I squared is a negative 1. And so really what we have is 16 plus 49, and that gives us the real number 65. And so we're going to use this fact that we can multiply conjugates and get a real number in order to get a complex number, or an I, off the bottom of a fraction, out of the denominator. Similar to FOILing it out, we had a shortcut for conjugates. It still works. We had the shortcut that says a plus b times a minus b equals a squared minus b squared. And so if I use that shortcut again, my a is 4 and my b is 7i, and so I would have 4 squared minus, well, let me put that in parentheses, 4 squared minus 7i in parentheses squared, which would give me 16 minus 7 squared and I squared, which equals 16 minus 49i squared. But again, I squared is negative 1, so that's 16 plus 49. Well, I shouldn't skip a step there. It's going to be 16 minus 49 times negative 1. And that gives me 16 plus 49, which still gives me 65. So you can use the shortcut, and again, I wrote a lot of steps in there. There is a way to shortcut a little bit with conjugates. And let's look at that below. It says the conjugate of a complex number is a plus bi is a minus bi. The conjugate of a complex number a minus bi is a plus bi. So if it's minus, the conjugate's plus. If it's plus, the conjugate's minus. The multiplication problem that we just performed involved conjugates. The multiplication of conjugates always results in the real number, and we're going to figure this one out. If I took a plus bi times a minus bi, I would get the first term squared, a squared, and I'll probably put that in parentheses. Let me rewrite that. A squared minus bi, that whole thing, squared. A squared minus bi squared. Well, again, squaring bi would make, I can get rid of the parentheses on the a squared, so we'd have a squared. We'd have minus b squared I times I squared. But we know I squared is negative 1. So we have a squared minus b squared a squared minus b squared times -1, which becomes a squared plus b squared. This formula is the formula that works for the conjugate of complex numbers, the a squared plus b squared. But there's a trick to it. You don't use the I in this formula. So in this formula, the I squared is not part of it. It's not part of this formula. Meaning, I guess another way of saying it is we've already used the I squared to make this thing plus. So you don't have to, when you're multiplying by the conjugate, you don't have to worry about putting in the I squared. You just use the coefficient in front of the I squared, whatever the number is that represents b. So let's put it to use in example 5 on the next page. We're going to divide and simplify to the form a plus bi, and this is important because there's going to be one extra step in order to put it in the form a plus bi. You got to have real part plus imaginary part in these problems. The first thing is we have a complex number on the bottom. So we know we're going to take that and we're going to multiply by the conjugate, and in this case the conjugate is 2 plus 5i. And we're going to multiply that on top and on bottom, 2 plus 5i. Which means on bottom we can use our a squared plus b squared formula. So that would be 2 squared plus 5 squared. And again, I don't worry about the I in that conjugate formula for complex numbers. On top though, we got a FOIL. So we're going to take 7 times 2, that's 14. We're going to need a bigger spot here. And then we're going to take 7 times 5i, that's plus 35i. And we got to take 4i times 2, that's plus 8i. And we're going to take 4i times 5i, that's going to give us plus 20i squared. And if we simplify, we can combine the 35 and the 8i. So what we're going to get over here would be 14 plus 43i and plus 20. And we can take the I squared and make it a -1. All over 4 plus 25. Well, 20 times -1 is minus 20, so we really got 14 plus 43i minus 20 all over 29. And we can take the 14 and we subtract 20, we're going to get -6 plus 43i over 29. Now, that's simplified, but it's not simplified into the right form, a plus bi. We have the 29 underneath both the real and the imaginary part, and what we have to do is split that up. We have to take the -6 and divide by 29. That's the real part of the complex number. And then we got the imaginary part, which would be 43i over 29. And you do have to make sure when you do this that you can't reduce these things. And in this case, we can't reduce it, so that's our answer. Try your checkpoint, and I will warn you, you will have to reduce your answer. When you come back after pausing, I'll give you the answer. Okay, the answer for checkpoint 5 is 18 over 25 plus 6i over 5. Okay, let's look at example 6. Still using conjugates to divide complex numbers. And in this case, we only have a 3i on bottom. So you don't have to use a conjugate in this case. You only have to multiply by what's on bottom. We're going to have to Well, actually, not the whole thing. We only have to get rid of the I. And we know that I squared is -1. So we can just multiply by I in this case on top and bottom. That would give us an I squared on bottom and would get rid of the complex part of this problem. So if we did that, we'd have to distribute the I on top. So you'd have 5I squared minus 4I. And on bottom I'd get 3I squared. Well, 3I squared is just 3 times -1. And 5I squared is 5 times -1 minus 4I over 3 times -1, which gives us -5 minus 4I all over a -3. Now we have to split this up. So we have -5 over a -3 and a minus 4I over a -3. And we can simplify this a little further because a negative divided by a negative on the 5 and the 3 is a positive, so that's positive 5 over 3. And the -4I divided by a -3 is a positive 2, so it would be plus 4I over 3, and that's our answer. Try your checkpoint. When you come back, I'll give you the answer. Okay, the answer to checkpoint 6 is -1/2 minus 3I over 4. Let's go on to example 7, and we're talking about simplified powers of I. Okay, so up at the top here, simplifying powers of I. It says express the given power of I in terms of I squared. That's how we're going to start it. So everything has to be I squared to some power. We're going to change what we have. And then replace the I squared with -1 because we know I squared equals -1, and simplify. It says use the fact that -1 to an even power is 1 and -1 to an odd power is -1. So let's see how that comes into play with example 7a. We got I squared. Now we're going to rewrite I squared as a power, or I'm sorry, we got I to the 12th. I'm sorry. We're going to rewrite I to the 12th as a power of I squared. So we're going to say, all right, this can be written as I squared, and then we're going to take half of the 12, which would be 6. So it would be I squared to the 6th. Okay, because if we multiplied these two, the 2 times the 6 would give us I to the 12th. So it's still equal to the same thing. And we know that I squared is really a -1. And the rule up here says, and we got I -1 to the 6th. It says -1 to an even power is equal to 1. So our answer is 1. For B, we got I to the 39th. Well, we can't cut 39 in half. So we can't write 39 as a power of in terms of I squared. But we can go one lower than that, 38. So we can rewrite this thing as I to the 38th times I. And I to the 1st times I to the 38th would make I to the 39th. 38, if we cut it in half, is 19. So we can rewrite that, I to the 38, as I squared to the 19th times I. And we're going to take I squared and make it a -1. So we got -1 to the 19th times I. And we got the fact that a -1 to an odd power equals a -1. So we got a -1 times I, which equals -I. So that's our answer for B. 1 was our answer for A. And C, 50 is even. So we don't need that extra I. You're only going to need that extra I anytime the power is odd. So yeah, anytime you have an odd power like 39, you're going to need the extra I. But 50 is even, so 2 is going to go into it. And so we would write it as I squared to the 25th, because 2 times 25 is 50, still equal. And we've got I squared as a -1 raised to the 25th odd power, and a -1 raised to an odd power is a -1. Pause here, try your checkpoints. When you come back, I'll give you the answers. Checkpoint 7, you got I to the 16th. That comes out to 1. for A. For B, we get I, and for C, we get negative I. That's all for 10.7 Part 3. I will see you in class to give you your work.